Hey guys, in this video we're going to learn how to evaluate limits. And right here we have our first method, which is called direct substitution. And we have the example limit as x approaches 3 for 2x plus 5. So if we wanted to use direct substitution to evaluate this limit, all I would have to do is plug in 3 into my x value. So let's do that. 2 times 3 plus 5. So all I'm doing is replacing my x with 3. So 2 times 3 plus 5, that's 6 plus 5, which is 11. So the limit as x approaches 3 for the function 2x plus 5 is 11. So this is direct substitution. Let's look at our next method to evaluate a limit, and this is called factoring. And I'll explain in a moment why we need this method. So let's say we had the example, the limit as x approaches 2 for the function x squared minus 4 all over x minus 2. Now, if I use direct substitution, replacing the x's with 2's, I would get 0 over 0. So 2 squared minus 4 all over 2 minus 2 gives me 0 over 0. Now, remember, this is a fun fact. 0 over 0, this is called an indeterminate. Indeterminate. So that is our term for 0 over 0. So since it's not a real number, we have to use something called factoring. So what I'm going to do is factor this numerator over here. So when I factor x squared minus 4, I'm going to get x plus 2 times x minus 2 all over x minus 2. And this is very important. Don't forget to include the limit. So the limit as x approaches 2, and then you're going to write your factored format. Okay, so now that I have my factored form, I can cancel the x minus 2's. So now I would have the limit equals the limit as x approaches 2 of x plus 2. Now I can use direct substitution where I plug in 2. So this would be the limit as x approaches 2. And then I would plug in 2 for x plus 2. So 2 plus 2 is 4. So my answer would be 4. Let's look at another form of evaluating a limit. And this is called rationalizing the numerator. Rationalizing the numerator. Okay, so let's say we had the example, the limit as x approaches 0 for the function radical x squared, or just x plus 1 minus 1 all over x. So if I use direct substitution, again, let's try it out. So I would have 0 plus 1 minus 1 all over 0. And then this would be square root of 1, which is 1. So 1 minus 1 over 0. And this would be 0 over 0. And we have our indeterminate again. So we're going to use something called rationalizing the numerator. And this requires us to multiply by the conjugate. So remember, the conjugate is the same thing but with opposite sign. So the numerator times the conjugate, so which is x plus 1 plus 1. So the conjugate, again, remember, is the same thing, but you change the sign. And we're going to do the same thing for our denominator. So x square root of x plus 1 plus 1. So when I multiply this, I'm going to get, let me remove this to the side or just delete it. Okay, so when I multiply this, I would get the x plus 1 minus 1 all over x. And I'm not going to, multiply this, and you'll see why in a moment. So all I did was just factor everything out. So this and this and this and that, or -1 times +1. So I just FOILed it, and this is what I would get. So once I have this, I can simplify this further. So x plus 1 minus 1, that gives me x over x times x plus 1 plus 1. And don't forget the limit notation. X approaches 0. And I would have the same thing over here, but I'm just going to make this my side work. So limit as x approaches 0. So now I could simplify this part further, so I can cancel the x's. So x and x cancel out, and I get the limit as x approaches 0 is 1 over the square root of x plus 1 plus 1. Now I can substitute 0 in for x, and I would get the limit as x approaches 0 is going to be 1 over, or I don't really need the limit here, so I get radical root 0 plus 1 plus 1. So this would give me 1 plus 1, so 1 over 2. So the limit as x approaches 0 for the function 1 over square root of x plus 1 plus 1 equals 1 over 2. And that's how you would, evaluate the limit using rationalizing the numerator. And the last one we're going to talk about in this video is called limits at infinity. Limits at infinity. So let's say you had the example limit as x approaches infinity for 3x squared plus 5x all over 2x squared minus x plus 1. So when you have limits at infinity, again, if you substitute, you can't really substitute 0 or any number in to see if you get a determinant. So what do? You're going to multiply. You're going to first identify what is your highest degree, and that's x squared. And it's on the numerator and the denominator. So all you're going to do is multiply the top and the bottom by 1 over x squared, because x squared, again, is your highest degree. 1 over x squared. So this comes out to be the limit as x approaches infinity of 3 plus 5 over x all over 2 minus 1 over x plus 1 over x squared. Now, if I plug in infinity for the x values, you kind of have to think about it in a logical way. So let's say we had 5 as our numerator. Is 5, okay, and I put the number 1. This equals 5. 5 over 2 equals 2.5. And you can see the numbers get smaller and smaller as the numbers increase. So this would be 0.05. So you see, as the denominator gets bigger, our value gets smaller and smaller. So it's trying to approach 0. So as the x value approaches infinity, these values over here are going to approach 0. So we can think of it as equaling 0. And we can simplify this, and we would get the limit as x approaches infinity to equal 3 over 2 for this function. So 3x squared plus 5x all over 2x squared minus x plus 1 equals 3 over 2. And there's another form for evaluating functions limits, which is called L'Hopital's, but we'll be talking more about that in our next unit. So these are our 4 ways to evaluate a limit: direct substitution, factoring, rationalizing the numerator, and the limits